For this scenario, I want to show that we can apply the ideas of simple harmonic motion to the pendulum under certain assumptions. Now, to do that, we first need to figure out what is going on here physically, set up an expression that says what are the forces or torques going on in such a case, and see if we can still get simple harmonic motion out of that. So first thing we want to do with this sort of drawing, we have a mass at the end of some, say, string in this case of length L, and we might start at some angle, and we imagine it's going to swing back and forth, as we know pendulums tend to do. So first thing we want to consider is what are the forces involved, and see if we can try getting a differential equation out of that like we did for the simple spring system. Now we expect there to be the force of weight downward, and we also know that there's going to be a tension force acting on the mass in this case. So we know the thing's then going to just kind of oscillate back and forth on us. But to describe that motion, we could describe it either with position, like x and y, or in this case might be better to use something like radial coordinates, and so we care much more about the angles involved. And if we're going to talk about angles, we might want to change how the angle changes, so like angular speed, how the angular speed changes angular acceleration, and we remember that there's a relationship between angular acceleration and torque. So that remember that the sum of torques on a body is equal to alpha times moment of inertia. So in this case, first, the moment of inertia, I, is going to actually be fairly simple in this case. If we treat the ball at the end of the string there as just one point mass, then the moment of inertia of it is just simply the mass of that ball and how far it is away from the point of rotation, which is length L, so this is just mL squared. Nice and simple so far. Now we have two different possible sources of torque. We could have torque from the tension, but since we also know that torque is related to the angle between the applied force and the lever arm, and we see in this case that the tension force is right along the line of the string, so we know that actually there is going to be no torque from the tension. So we know this is just 0. On the other hand, the weight force we have here is not parallel or anti-parallel to the string, but it's also not exactly at 90 degrees either. It's going to be at something just a little bit different than either of them. So it's only going to be a component of the force of gravity that is perpendicular to the string and giving us maximum torque. So in that case, we actually could see that the torque from the weight is going to be mg sine theta, and then multiplied by the length of the lever arm, in this case, length L. So there's only one source of torque, and we'll apply that torque as mg L sine theta equaling to alpha times the moment of inertia, which we said was mL squared. And we can do a few things to simplify. We see that the mass terms will cancel out. One of the length terms will cancel out. And since we also know that acceleration, the angular acceleration, is actually 2 time derivatives of theta, so I'll call it theta double dot, we see that this actually will simplify to g over L sine theta is equal to theta double dot. And one other thing that I should emphasize as well that I didn't do before is that the torque involved is, in this case, designed actually to make that angle smaller. If it starts at a large angle, it wants to go to a small angle. So actually this torque should be a negative torque. Introduces a minus sign here, and here. Now, so far this might look a bit similar to the differential equation that we had for the spring. We see that we have two time derivatives, we have some constant out front, we have a minus sign, so it looks similar except that this is a sine of theta rather than just theta equals theta double dot and then some constants involved. So this isn't quite simple harmonic motion yet. So if we just focus in on the sine function itself, there's a few things you might have noticed that if theta is 0, sine of theta is 0. So in that case, if you're very close to angle 0, you'd also expect then maybe sine of that angle to also be very close to 0. Now, I won't demonstrate this fully, but it's actually interesting that for small angles, that sine of theta is approximately equal to theta. And this is if we're doing this in units of radians. And this is usually a pretty good approximation for angles of less than 1 radian, or maybe several degrees, 10, 15 degrees at most. This will be a pretty good approximation. You can start punching into your calculator to see how close they are, but for most angles this means this will be fine. So if we have relatively small oscillations around some sort of equilibrium point, then we can apply this approximation. And if we do that from our previous equation, that we said that negative g over L sine theta is equal to theta double dot, we can now approximate that to give us negative g over L theta is equal to theta double dot. And now you can see that this is the exact same form of what we did when we did the simple harmonic oscillator. All we have to do in this case then is say that our omega value is equal to the square root of g over L. And we can get the same sort of forms as we did before. In this case, we'd also be able to say something about this pendulum, that the period, remember, is supposed to be 2 pi over omega. So we know the period is going to be 2 pi square root of the length of that pendulum divided by the acceleration due to gravity. And this is a nice general result. The only thing we could do to further complicate it is if we didn't have a simple pendulum, but we had a pendulum with a more spread out mass. Now, where does that come into? Now, remember I had said before something about the moment of inertia I, and in general, that has the definition of every little piece of mass, how far it is away from the point of rotation squared. If all the mass were just at one point, then this is a very simple summation. But if we have a more complicated object, then we might have a little bit more work ahead of us. And this might make it so terms don't cancel out as nicely. But for the most part, what this will do is just change the result we have for omega, the angular frequency, by some fractional amount in the square root there. So this, like I say, is an additional complication, but the exact same math is involved. So if you wanted to go back and set this up again, you should be able to get very similar results.